startup. Part of our team slash Techstarter mission is to increase accessibility to the outdoors for individuals with physical disabilities, and we also strive for our products to be efficient and very affordable for our clients. I'll be handing the mic off to my deputy Mary.
We often found that wheelchair users have to decide between outdoor accessibility and indoor convenience. Outdoor wheelchairs are too expensive for most users and too bulky to be used indoors, whereas indoor wheelchairs are compact and cheaper, but drastically uncomfortable on uneven terrain. We found that no wheelchair exists that combines the benefits of both without also incurring the drawbacks. Which led to our research and design question: how can we eliminate the need for two separate wheelchairs by combining an indoor and outdoor wheelchair all in one design using NASA technology? To start off the engineering design process, our team decided on product goals, which determine the design parameters. For convenience, our wheelchair needs to be comfortable on outdoor terrain and as compact as an indoor wheelchair. The transition between indoor and outdoor modes should take less than 5 steps and be comfortable and be intuitive to use. To be used independently, our transitioning mechanism needs to be lightweight to minimize the strength required by the user and can be operated entirely by the user without assistance. To maximize our product's accessibility, thus furthering the impact of our invention, we aim to reduce the materials and manufacturing costs with $300 per pair of wheels to and we wanted it to be able to function in -20 to +50 degrees Celsius to be used across different regions.
So the NASA technology that we utilize for our project is called shape memory alloy tubular structure. Shape memory alloy has the remarkable ability to return to its predefined shape after being bent, as seen in this NASA animation. And NASA successfully utilized shape memory alloy for their rover wheels, tire trucks, tires, and for bike tires as well. And in being inspired by their adaptive properties, we decided that it would be the best material to implement in our all-terrain wheelchair application. So in order to successfully implement the SMA into our design, we needed to design a custom super elastic shape memory alloy sheet. And in order to do so, we needed to implement coiling in order to successfully do space efficiency and terrain adaptability. So in terms of terrain adaptability, the coil design allows it to have ground contact support and be able to retract back into the wheel efficiently. The material that we chose is nitinol, a combination of nickel and titanium, often used for medical applications such as stents or NASA's rover tires that are now being developed. So additionally, we designed 1 to 2 millimeters of diameter springs in order for structural support for the wheels, as well as we trained it so that it would be implemented or function in the temperature of in between -20 degrees Celsius to 50 degrees Celsius range in order for it to have the capability to be used in multiple different environments.
Initially, we had 3 different design ideas. We had the octane drivetrain, pneumatic supports, and internal tire. We ended up going with the internal tire since it maximized our design goals of convenience, independence, and accessibility. Our additional designs have the SMA sheet held within the tire, and it could be rolled around the outside to convert from indoor to outdoor modes. When it's stored on the inside, it works as an indoor tire like you see on a normal wheelchair, and then it shows that it's completely self-contained and shows that it's very effective in its packaging and size for containing both wheels in one. Our very first iteration, seen on the left, had the sheet, and it was high friction and would jam a lot. And so on our second iteration, we wanted to reduce the friction. And so we looked into having a ball bearing inspired track, and that would reduce the friction, but unfortunately we ran into problems with the changing curvature of the track, which led to the development of the 2-dot system. And the two-dot system, so usually sliders can only travel on a curvature of a single radius, but ours is a spiral, so it changes throughout it, and which causes problems. The two-dot system, the beauty of it is that it slides on two rapid points, and that allows it to travel on any curvature rail. And it can even go through changing ones, like our spiral. And that brings us to our current design after solving that problem, which I'm holding right now, with four key components: the SMA sheet, the sliders that hold the SMA, and the plug, which will fill in the gap on the outside and complete the wheel, and the crank, which is what moves the sliders in and out between the two modes. And we are able to hold the sheet onto the prototype through converting the entire frame into a rail system. So this entire black part spiral is the rail that it slides on, and the plug can be removed, and then it creates a gap for it to pass through the outside of the circle, and the crank will be used to deploy it in and out and switch between the modes. And that's how we combine an indoor and outdoor wheel through the benefits into one single design and mechanism.
So once the prototype was complete, we wanted to look at, did this actually meet that initial design parameters and criteria we set, right? And we found that yes, we were able to complete a design that hit every single one of those initial parameters. So first off, the cranking gear system allowed it to be completely independent for the user. Along with that, it also provides a seamless tire switch between our tire modes, right? Along with this, we have a lightweight design due to it being very efficiently packaged and therefore requiring less materials. And needing less materials for this design also makes us more cost effective as a company, in turn allowing us to be considerably more cost effective for retail and overall reducing costs so that more customers have accessibility to our products. Thank you. So a lot of work was done in just one semester. This is our first semester doing this project. We're very proud of everything we've gotten done, but there's certainly a lot more to be done. Our first step is finite element analysis, which just for time constraints of this project, we decided not to cover in depth. But if anyone has questions, I would be happy to talk about it. So first off, we definitely need to get the FEA done. And then following that, we'd like to reiterate the design further and continue to improve on what we already have. And then actually manufacture and test this product with SMA to ensure that the SMA performs the way that we expect it to. And finally, we'd like to finalize our business plan and actually pursue this as a genuine tech startup. So we'd like to thank our advisors, and especially TSGC, for hosting this event today and providing us this opportunity. Our QR code can be scanned if you'd like to see our references, and we'd love to take any questions you have now. Thank you.
Hi. So I was wondering, for when you had it in the indoor configuration, did you run into any trouble with, because of course there's that slight gap where you're allowing the treads to come through. Did you have any trouble with that? Did you make any sort of design changes specifically to help with that?
We weren't able to bring it today, but there is the plug that would connect to both sides, and so it just slots in and would cover that gap, and it would have the rubber on the outside, so it would complete the circle and make it a full wheel.
Okay, awesome. Thank you.
Other questions? I know you said you wanted to pursue this as a startup. Have you guys submitted patents?
No. But we will. We plan on looking into it very soon.
Have you taken into consideration like the fatigue line, the cyclic fatigue for the estimate?
Yeah, so as a business model, we started taking into consideration SMA over time does degrade, as you just mentioned. And we had quite a few different thoughts on that. Obviously, maintenance is going to need to be a part of the package. Because the actual deployable sheet can be completely removed, we were debating a couple of options. One is selling just the sheet so the user could just rebuy. But I also think as a business model, it might be smart to do subscription service. So either you could just buy the sheet or you pay like kind of a warranty and then you would have someone come out and fix the whole thing for you. So those are our two options. We're not positive which one we'll pursue. That's right now though.
All right, check out the team at their booth. We'll move on. Thank you, team.
Next up, please welcome Team Sidekick. All right. Hi, everyone. I'm Ryan, and I'm here to talk about our project, Sidekick. So earlier this semester, we got the opportunity to take on a TSGC challenge as part of our capstone. We, because of our backgrounds, decided on a topic that was focused around robotic mobility on extraterrestrial terrain. And to sort of get a better idea of how this would actually work, we went down the road and spoke to a professor at our Geosciences Institute. And he studies the presence of ancient lakes on Mars by analyzing topological and compositional data from the Mars Reconnaissance Orbiter, specifically high-rise data. Using that information, he's able to extrapolate a lot of the stuff that he has from his reports. He also uses rover data. The issue is that oftentimes the rovers are unable to access some of the most interesting geological formations because of the change and the variation in geometry. So we developed a solution for that, and to talk about that more is Daniel. Oh yeah, sorry. This is an example of some of the data that they'd be walking through. So the strata on here, each layer is going to tell a story. Some layers will only be developed and formed in the presence of liquid water on Mars. I should have said that earlier.
Thank you, Ryan. So as previously mentioned, a lot of this unharvested data on Mars exists in these areas that are not exactly accessible to these current exploration rovers. So our approach to this is we want to target certain physical attributes within our design. We want Sidekick to be much lighter, much smaller, and much cheaper than current exploration rovers are. But we also want Sidekick to use a advanced mobility system to get around these craters and cliff faces, as well as a umbilical connection, which allows Sidekick to transmit data, draw power from the main system, as well as tether itself to the main system while it performs its mission. So at the very moment, Sidekick is comprised of 4 main subsystems. We have a frame chassis, payload suspension, arm and drivetrain, and electronics and controls. Here to talk a bit more about our frame and chassis is Austin.
Thank you, Daniel. So the frame consists of 4 aluminum bars. The left and right ones are going to be 6061 hollow aluminum bars. Inside of those bars are going to be 2 motors, 1 each. They're going to be placed diagonal from each other, so one on the top left of this image and one on the bottom right. They will translate motion using a bevel gear. The top and bottom bars are going to be 80/20 aluminum extrusions. These aluminum extrusions are hollow as well, and they will allow a shaft to travel through them. That shaft will actuate as a result of the perpendicular motion from those bevel gears. In the center of this is a central aluminum extrusion again. That central aluminum extrusion has other protruding extrusions that will house the payload and spring system. Along those, there will be a spring that will dampen oscillations as we go. Introducing Connor to talk more about that suspension and payload.
Thanks, Austin.
So yeah, as you can see, we've got our payload here housed within the chassis and frame system. Currently, it's made of wood and acrylic panels because that was what was readily available at our makerspace. Right now, it just houses the electronic system, but eventually we'd like to have it house actual instrumentation that the scientists would want to bring down into these craters. And of course, instrumentation can be pretty delicate, and what we'd like to do to combat that is to have a suspension system built into the payload. So that's the right image right there. You can see a spring on the top and bottom of the central bar that Austin mentioned. And sandwiching those springs are the top face and bottom face of the payload. So when you experience like rocky drive over rocks or the crater face, the springs, because they're made out of this flexible filament, custom printed with that diamond design, they'll stretch and compress based on the sort of forces that you're feeling, and so it should hopefully dampen the vibrational forces. Now, here to talk about the actual movement of the rover is Matthew.
Cool. Thank you, Connor. So our drivetrain actually consists of 4 independent actuating arms, as previously discussed. Each arm has a shell that's machined out of 6061 aluminum. You can kind of see that up in the top left picture. After we successfully machine those, each one of those shells can house a high torque motor. This allows for controlled drive with precision, since we're dealing with very tough terrain that we want to make sure we don't mess anything up. Attached to those motors are bevel gears that translate the motion perpendicularly to the axle. You can see that on the GIF playing the wheel rolling. And attached to that axle is our wheels, which comprise of 2 different components. The rims, which are made out of a tough plastic to support the weight of the robot, and then compliant material that was used for the springs as well for the tires to allow for more compliability in that area.
So it takes a lot of work to actually get a lot of those mechanical parts working in tandem. To accomplish this, our prototype uses a 110 volt power supply. That way we can just plug straight into the wall. And off of that, we're able to run all of our 12 volt and 5 volt components. So the 12 volt components are primarily the 6 motors, 4 drive motors, and then 2 in the arms. All of the logic for that is controlled off of an Arduino Mega. So that's plugged into all of our motors, all of our sensors, and that's doing a lot of the processing. In tandem with the Arduino Mega, we have 2 more microcontrollers that are ESP32s. One of them is constantly reading Bluetooth output from this PlayStation controller, so it'll read all of the button states. The other is set up as a Wi-Fi host, so someone with a mobile device can actually connect to the prototype and read metrics off of that remote using their phone or laptop. This is sort of a general outline of how the electronic system is designed to be set up right now. If you are curious, I encourage you to go take a visit and ask some questions at our stand later.
So with all subsystems integrated, we created our first prototype. If you take a look at that top left-hand image there, we have our first CAD assembly with all systems integrated. You'll notice that right bar is transparent. That's the frame I was talking about earlier. In there is one of those motors that will actually actuate both of the arms on the left-hand side together. And in doing so, you increase that angle, and thus you can manipulate the ride height of this vehicle. If you go down one image, we have our real-world prototype. So very similar with slight tweaks during integration, whether that be through brackets, quick fixes, or such. If you go to the top right image, that's an image during integration. So with an open top, you see the electronics housed in there and the process that we use to get them there. And then lastly, the bottom right image is our drivetrain functioning as expected, reading inputs from that PlayStation controller.
So much like Lone Star College, this is our first semester working on this, and we believe we actually have a small.
I think it's trying to connect to the Wi-Fi.
Sorry, get it back in there. There we go. Awesome. Back on. Okay, sorry about that. So yeah, it's our first semester doing this. We have a small laundry list that we believe that we kind of accomplished throughout our semester with this. So as of right now, we have a successful drive test going. We also were able to fully make that connection between our controller and the onboard control system. And we've also been able to simultaneously run all 6 motors, so we can actuate the arms and also spin the motor, so it works in that situation. We've also been able to implement that passive suspension system within our payload to maintain that stability during travel. And we've effectively housed all our subsystems within a pre-designed chassis that we came up with earlier in the semester.
And for our future, we have plans to improve each subsystem of our design. For the frame and chassis, we'd like to fully develop the umbilical cord system, so we can hopefully test an enchanted rock in the end of the month. And then in tandem with that, also develop the test or work more with the wheel and develop that to be a better design and be able to work on more extreme terrains. And then for the payload, we're going to improve the electronic accessibility, and kind of with that, with our control system, kind of collapse our electronic system into a PCB so it's more simple and streamlined.
All right, and then special thanks to our faculty advisors. We'd also like to thank Dr. Timothy Urban and all of TSGC. for hosting us. And then finally, we'd like to thank our course instructors and our TA for helping us throughout this quick semester. Thank you for listening, and if you want to see more of it, you can come to our booth. But feel free to ask questions now.
Yeah, I have a question about Article 2 and wireless control over there. I use PS5 controller as an example. What is the other controller you can use? That's the Switch control, the Xbox One control, anything?
Why I went with the PlayStation controller specifically.
Yeah.
So the PlayStation controller was selected specifically because A, I owned one already, and B, there was a lot of online documentation about how to accomplish reading off of all of the controls to the serial monitor, and that was an essential part of getting this electronic system to work consistently. Yeah.
Quick question for you. How did you account for the lunar regolith clumping on the wheels in your design?
So maybe we didn't make it super clear. This is purely just a Mars rover, but of course like would be regolith, not actually regolith, but just rocks and stuff on Mars specifically. And since it's a crater face, it actually wouldn't be experiencing any sort of pebbles or like granite or anything like that. It's just a very like solid surface. That was something that we learned from our geoscientist faculty advisor. We were trying to be prepared for like specifically the wheel design, and then he said that fortunately, because we're specifically driving on these crater faces and it's vertical, the erosion kind of smooths it out. So yeah, in this situation, we didn't have to worry about that. Thank you.
All right, thank you, team.
Good afternoon, everyone. We are Team Astro Apollo. My name is Julio Pinzon. I'm here with Alberto Leon, Guillermo Torres, and Diego Salazar to present our softwoods attachment device. So to give a bit of an overview for our presentation, I will go over the project background, our goal summary, then Gil will go over the criteria and constraint, closing standards, and house quality. Then Alberto will go over our concept design and our Astro Touch V2 design. Then Gabriel is going to go over the modeling and analysis and our technical content, and I'll close it up by going over project work plan and future works. So first of all, what are softgoods? Softgoods are strong, lightweight, flexible fabrics that can withstand and endure extreme temperatures. They play a crucial role because they protect the spacecraft and also the astronauts. And they're used for multiple components such as EVA suits, satellites, airbags, and inflatable habitats. So our goal was to design a tool or set of tools that was capable of attaching overlapping pieces of soft goods from only the outer facing side, while keeping in mind that astronauts have limited mobility and dexterity in their spacesuits. Our goal was to design a tool that was reliable, easy to use, and effective at doing this task. Now I'll pass it on to Gil to go over the criteria.
Thank you, Julio. So the maximum value of tools allowed was three, which altogether cannot exceed a weight of 10 pounds on Earth's gravity, and it must fit within a stowed volume of 12 inches by 12 inches by 12 inches. Additionally, it needed to be manually powered, either linear or rotational mechanism. Also, it needed to either sink or be neutrally buoyant in water. Next, it needed to be EVA compatible and have materials approved on the NBL approved list, such as the metals and 3D printed parts we were using. Some safety criteria that we had were it needed to pass an ultimate stress test of exceeding a factor of two. Also, it needed to have a 1-inch tether point attached to it, and it couldn't have non-functional sharp edges, and any non-functional sharp edges needed to be covered when not in use. We needed to make this device to fit within a $500 budget range. Next are coding standards. The main standard that we had to satisfy was NASA standard 6030, which was for safety and reliability for 3D printed parts and space missions. Next, we created a house of quality, and we used that to evaluate all the different prototypes that we had. And based on the engineering metrics, we selected Astro Attach V2 as the best option since it had the best ergonomics compared to the other prototypes. I'll be passing now to Alberto to talk about the external design.
Thank you, Gil. So here we have the Astro Attach V1. It was our initial prototype design at the beginning of the semester. As you can see, it was designed to accommodate an EVA glove with an enlarged grip area in the center. It also, in the middle, it has a grip with a stipple texture to allow a comfortable hold and grip in microgravity conditions. It also has an outboard stapling mechanism for operation. The device dimensions are 11 inches from the front of the housing to the end of the handle, with a height of 8.3 inches and a width of 2 inches. After 3D printing this device, we got an in-hand feel how this device looked and felt, and we noticed a lot of issues. First, it was too large in size, and second, to actuate, it was very uncomfortable without a glove, showing that we needed to do something more compact, which led the team in a different direction to develop the Astro Attach V2. It is more compact and portable, with a 40% decrease in overall size compared to version 1. It also has a redesigned handle for an improved grip and comfort to accommodate our forward action stapling mechanism. It is lightweight and 3D printed of PETG with an assembled weight of 0.6 pounds. It is compatible with 1/4 inch staples and 3/8 inch staples with a max staple capacity of 100. The dimensions of this device are 7.2 inches from the front of the housing to the end of the handle, with a height of 6.3 inches and a width of 0.8 inches, with a 1-inch tether point at the bottom. And the maximum grip length area of the device is 3.1 inches to allow enough room for an EVA glove to wrap around our device and use. Moving on to the internal design of the Astro Attach V2, it consists of 6 key components. And the way it functions is once the handle is actuated, the push arm inside the handle comes into contact with the sear. This sear then compresses a conical spring while simultaneously retracting a staple driver. After the sear runs out of travel, the sear releases the staple driver along with the conical spring in the center, propelling the staple driver forward to dispense a staple and securely attaching the soft goods. I will now be handing it over to Gabriel to speak about our modeling and analysis.
Thank you. So for the modeling and analysis, we chose to do it on the handle since this is a critical component of the Astro Attach. The moment came out to be 110 inch-pounds, so the force at the contact area was 42 pounds. With respect to the contact area, the stress is about 295 psi. The PETG yield strength is 5,800 psi, so the factor of safety was 19, so it's pretty far from yield. For some technical content on the Astro Attach, the max number of tools that was allowed was 3 pieces, but the Astro Attach was 1 piece.
Also, it couldn't weigh no more than 10 pounds on Earth. The Astro Attach is 0.6 pounds. The volume had to be within 12 by 12 by 12, and the Astro Attach is 7.2 by 6.3 times 0.8 inches. It's a linear actuating, and it's a approved material PETG, and it has a 1 tether point. This is the bill of materials of the Astro Attach. The highest cost item was the print time, $997. It was the print time, $120, but the total cost is about $245. I'll go ahead and pass it on to Julio for the project work plan.
So here we have our Gantt chart that we basically used to keep track of any deliverables that we needed to complete to finish our project. And go on to our future works. What we want to continue doing is we want to develop a test fixture to evaluate the performance of our device. We also want to experiment with other types of staples just to make sure that the soft goods stay together. And we want to continue to do more analysis, such as a life cycle analysis and also a durability test on the housing itself. And that's it. If you have any questions, go ahead. Thank you.
Questions? Somebody's got to have a question.
I have a question.
What's the biggest constraint y'all had coming from last semester into this semester with the new model that y'all have designed?
That's a really good question. It was a challenge to get something from being conceptual to physical. It was a learning experience. One thing that we had a benefit from was 3D printing. So it was like rapid, any design we made a change with, we were able to print within the same day. But I would say the biggest constraint was just the tolerances, adjusting one little thing to throw off the whole mechanism for it to function. And just trying to stay within those guidelines of being compact and having everything to work at once was our biggest challenge. We're still tackling that at the moment. But overall, we've enjoyed the experience of participating in this competition, learning from semester 1 to semester 2, and seeing our conceptual design coming to life and being able here to present it. So thank you for that question.
Any other questions? All right, thank you, team. Quick break. You can take your seats again. We will wrap up our afternoon presentations. All right, good afternoon. Please take your seats. We are going to start our last session now with Team Daedalus.
Hi everyone, we're Team Daedalus with Texas A&M. My name is Camden Redden. This is Emily, Sarah, and Anushka, Samit, and Ayan.
And now this thing's working too. So now let's go ahead and get started. On the ISS currently, there's no way for astronauts to launder their clothes, and so they have to reuse their clothing up to a couple weeks at a time and have to dispose of the clothes after. Now, for ISS, that works just fine. We can send new clothes up, but for a lunar mission, that is much more non-feasible, and so we need a laundering system. And so we set out to tackle that challenge by optimizing current laundering techniques and combo washer dryers.
Now, for this challenge, we had to go by the design goals of optimizing mass and energy efficiency, as well as the design challenges of 1/6 of Earth's gravity, along with the inability to vent hot air out into the environment.
There are two main types of terrestrial machines, top loaders and front loaders. We analyzed about 200 terrestrial machines and determined that front loaders are 45% more energy efficient, use 50% less water, and tend to be more compact, making them better for our system.
Here are the 6 main design differences from a terrestrial model to our lunar design. Instead of a steel drum, our design let us choose titanium. We altered the RPM values, went with a closed loop air system and a heat pump dryer, changed copper wiring to aluminum. Instead of steel motor bearing, we used hybrid ceramic.
For the drum, we're going to be using a RPM of 20 for the wetting phase, which is the minimal angular velocity necessary for an efficient tumbling under lunar conditions. For the dewatering process, we're going to be using a 1600 RPM, which is the maximum RPM that commercial washer dryers uses, which is because of the increased capillary action and also to compensate for a smaller drum radius. Also, the relationship between the angular velocity and drum radius give us a set of accepted values for the drum dimensions. When calculating the depth, we were able to get a volume for a washer with a maximum clothing capacity of 4.5 kilograms of clothes. And the final dimensions were made by the standard of 1 to 2 radius to height ratio of the average washer dryers.
Here is a trade study that we did on the material of the inner drum. The parameter that we considered the most was minimizing mass, which was specifically mentioned in our design goals. We looked at the most commonly used terrestrial drum materials, as well as a few unique composites, ranked them from 1 to 10, multiplied by the importance of the category. This led us to choose titanium alloy as our material, which has half the mass density of steel and has excellent properties for strength, corrosion resistance, and properties important to the drying cycle.
In the following simulations, you will be able to see the tumbling efficiency under Earth and lunar conditions, and you will be able to see that the tumbling efficiency under lunar conditions are more efficient under RPMs that are lower, from 80 to 10 RPM.
For the drying system, there are 4 main components we have to make sure we meet. It cannot vent air into the surroundings, it must operate at a low temperature, be energy efficient, and all the components have to be lightweight. So currently on Earth, there exist 2 types of ventless dryers, heat pump dryers and condenser dryers. We conducted a trade study to determine which one would be the most efficient for our system. We found that heat pumps tend to use 65% less energy than condenser dryers, and they also tend to operate at 55 degrees Celsius, which is 20 degrees Celsius less than condenser dryers, making them safer for use on a lunar base.
Now, in that heat pump, we were able to utilize the temperature constraint to our advantage. Because we're going with a lower temperature, we need a smaller condenser, which allows us to decrease the heaviest part of the heat pump. the compressor is on average 20 to 15 kilograms. We were able to scale it down to 9.5 kilograms, which is a large decrease. Now, in these images, you can see a dimensional sketch of our condenser, which shows you that it's to scale, and which our masses are to scale as well. And in the cross-section of the compressor, you can see how we have a electromagnetic clutch that allows us to use only one motor instead of two, increasing our energy efficiency.
We mirror the design of our electrical system with the design of the model itself, which is to find something compact, energy efficient, and with good heat management. And for that, we chose a permanent magnet synchronous motor as our motor, which gives us full control over heat and energy efficiency, as well as cuts down on space due to its compactness.
And then continuing along the theme of minimizing the mass, we swapped the copper winding with aluminum wire. With 1/3 the density and 2/3 the conductivity, it can make an effective weight-efficient substitute for the conductors. Now, that does come with a drawback, and that is that it requires more insulation and thermal methods in order to protect the higher resistances.
To conclude our design, we have a quick concept of operations of a typical 5-hour wash and dry cycle. The RPMs for each phase are shown, as well as the color and coding for the power consumption during each phase. Our final design has a mass of 44 kilograms and can carry a max load of 4.5 kilograms of clothing, as per our design goals and restrictions.
The budgeting of our prototype was quite efficient because we were able to reuse a motor from a non-functional front loader from one of our team members. Most of our money comes from the 3D printing. For the estimated cost of the final design, we got the average price of a commercial washer dryer and adjusted for modifications and also to the higher standards that NASA would require.
The design standards our model falls under are divided into two components: electrical performance and thermal management. For electrical performance, the wiring of our motor are under basic insulation guidelines, which help us avoid power overload. For thermal management, we went with the listed NASA standards to avoid burning our astronauts on accidentally hot surfaces and to avoid compromising surrounding equipment with heat radiation.
Now, in the future of this project, we would like to look into, for the heat pump, better seals and sealants for those systems, because a lot of the materials that are commonly used on Earth are subject to decay due to radiation over a long period of time. And so if we can enhance that, we can make it more sustainable for long periods of time.
And then within the electrical system, we would like to develop the wiring for the entire machine and then also a PCB to describe the behavior of the machine's rotations.
Due to the lightweight nature of our machine, we expect increased vibrations. And to counteract this, we want to do more research into vibration dampening techniques. One that we found promising was called frequency matching mass damping.
We would like to thank Tango Think Tank and the Texas Space Grant Consortium for their funding and support. Next, we would like to thank our NASA mentors, Mr. Michael Ewer and Andrew Ahrens, for their continued technical and design guidance throughout this process. Lastly, we would like to thank Dr. Homero Castaneda and Mr. Ulysses Martin-Diaz for their provided lab space. Thank you, everybody.
Question. Now, I saw how all the criteria picked was like relevant for like just normal washer operations. Like on the Earth, I would also follow these guidelines as well. But I didn't quite see like how would these how would the materials you chose like specifically be fit for the operation on the moon? For example, what specific parts of the washer are catered towards the 1/6 gravity?
So the 1/6 gravity doesn't affect the material too much. However, we do have an appendix regarding the materials. So for most of the parts of the heat pump, we would use aluminum 661. And then for the condenser and evaporator, we chose aluminum 663 because of its higher thermal conductivity.
The main consideration that we made for the different lunar gravity and forces accompanying that had to do with the RPM values that we chose for rotating the clothing. I think I have a diagram in here. So For the wash cycle and the dry cycle, the clothes are supposed to rise to almost the top of the drum and fall down at a 45-degree angle. This changes with the lunar gravity because the RPM opposes it. So a lower RPM is needed because of the lower gravity. So for the wash and dry cycles, we chose a lower RPM. Now, the lunar gravity also affects the capillary action of the water, which means that water is harder to remove from the clothes. So for the spin cycle, where the clothes are rotated very quickly around the drum to get the water out, we chose a higher RPM value of 1600. And those are the main ways that we accounted for the different lunar gravity. Thanks for your question.
In relation to the question, because of the low gravity, it's also may affect how fluids will act in low gravity conditions. Did you consider different or diameters of your pipes or over angles, and how the whole system will be connected to the overall system of the habitat, let's say?
So due to the lower gravity, it's much easier for the water to flow with a pump pulling it. And so our pipes are slightly bigger just for easier flow. And we use a diaphragm pump because of its durability and efficiency in a lower gravity environment.
All right, thank you, team.
Maybe we should mic them and use them. Like, shit, everything.
All right, next up, please welcome Interstellar Corporation.
Hello, everyone. My name is Brian Lopez, and I'm the team leader. And these are my teammates. Gerardo Garza, Alan Hernandez, Silas Lasso, Tristan Netherland, and Jaime Rodriguez. And together we are the Interstellar Corporation. And our topic is, stay with me now, the improvisation of general purpose robotic manipulation to human scale logistic maintenance, outfitting, and utilization. Several countries have sent out rovers to Mars to explore its terrain and find traces of water to one day colonize the planet. However, this is easier said than done. The planet's harsh environment and extremely cold temperatures, alongside its prolonged dust storms that are planetary, create a very unique environment for technology to survive. This is truly special for solar-powered systems. As a solar-powered rover traverses Mars, the recurring dust storms will slowly deposit a layer of electrostatically charged dust on top of the solar panels. This dust, as it is electrostatically charged, likes to adhere to surfaces, and it's very difficult to remove. This, as you can see on the opportunity, this was just a couple of years of difference. The solar panels almost look like the surface of Mars itself. NASA's previous rovers, the Spirit and Opportunity, had a 0.2% degradation per sol for 300 sols. This eventually led up to a 70% solar efficiency at a steady state for the duration of their missions.
To prevent the degradation of the solar panels, we decided to implement a dust mitigation system included within the rover. This allows for the solar panels to have a better efficiency over time. This led us to our project, which is the Endurance. Our model, the Endurance, has a size of 137 centimeters in length and width and stands tall at 92 centimeters. This has a feature which is the cleaning mechanism, which is retractable from the inside of the rover. This allows it to be both compressed and easily reachable. The next part of the cleaning mechanism is a brush arm. The brush arm both spins and rotates throughout the solar panels to be able to clean it.
This is directed by a real system included within the SAT size and the center of the rover.
There will be two cleaning mechanisms, one on either side of the rover. Each mechanism will consist of 4 motors and 2 linear actuators. Initially, the solar panels will act as a cover for the cleaning mechanism, preventing dust intrusion. Once deployment initiates, a separate motor will retract the 2 center solar panels, revealing the cleaning mechanism. The cleaning mechanism itself will then be raised into place and leveled with the solar panels via linear actuators. To be able to understand power requirements for the mechanism, to be able to power the system, we must first understand how much energy it requires. The solar panels we chose for the endurance will allow 1,200 watt-hours of energy per 8.5 hours of sunlight on average solar. Each actuator must travel 14.5 centimeters to raise the cleaning system fully. Once deployed, a stepper motor will rotate the brush into place and hold it there. Another stepper motor will drive the linear movement along the rail system. Both of these motors will draw 24 watts and consume 16 watt-hours of power per cleaning operation.
Alright, so the brush design was meant to be a rotating bristled brush made out of a cryogenic polymer called teak. Teak was also chosen because it can withstand Mars's environments. It won't be so abrasive on the surface of the solar panels, but mainly because it is able to keep its properties at such low temperatures, something that is crucial to this project. For example, its TG value. Additionally, the bristle will be infused with graphene, which will allow us to run a small electrical charge throughout the entire brush. This electrical charge will allow us to change the electrical charge of the polymer, allowing us to repel the dust as it sweeps through the solar panels. We did find out that such a charge can actually affect the solar panels, but we plan on implementing a layer of borosilicate glass between the brush and the solar panels as a protective layer. The brush will spin up at about 200 RPMs and will also be driven by another stepper motor, which will also require 24 watts, totaling 16 watt-hours per operation. Each cleaning cycle, including the deployments, the spinning, the traveling, and the retraction, will take about 45 minutes. And in those 45 minutes, it will require about 55 watt-hours, which surprisingly is about less than 10% of the total energy that is generated in one day by the rover. We anticipate the system we plan on deploying the system 4 times per Martian year to maintain its efficiency above 85%, but that is also that can also change if it's needed.
The endurance rover will primarily be made out of aluminum. Aluminum was a selected metal to use for its strength to lightweight ratio and also its high resistance to the harsh Martian environments. To ensure functionality of the cleaning mechanism arm, a finite element analysis will be conducted. The analysis revealed that with the lack of support on the spinning wheel side, a moment will occur. So with the moment occurring, we will have some sort of interference on the arm's operation. Knowing this, the endurance has been strategically designed to minimize any forces that could change the cleaning arm from its intended path. The specific track that we are using are guided tracks or guided trails to be exact. These guided trails will be implemented on our rovers at the end of the solar panels and also in the center of our rover. Um, these rails serve to constrain the movement of the cleaning arm, ensuring stable and precise operations.
As we move into the next semester of our project, we'll shift our focus from design to implementation. First, we'll create wiring diagrams for all the electrical components, and after doing that, we'll begin the coding of the cleaning mechanism to ensure the efficiency of the path across the solar panels. After that, we will start conducting the testing of the cleaning system to assess the performance under simulated Martian conditions. We're also looking into adding heating elements to protect against the cold temperatures and enhance the system's reliability, ensuring that it doesn't freeze up in Martian's frigid temperatures. Finally, with these systems in place, we'll start to conduct construction of the Endurance rover.
Lastly, we wanted to announce three of our professors, Dr. Larry Pio, Professor Margarita Hashikar, and Professor Isis Brady. If you have any questions, this is the time. References, if you care to check, they're on the QR code.
You have fibers on a rotating system that is touching another, that's basically touching another surface. Did you look at tribal charging as a problem?
Ooh, that is a great question. That's actually something we have yet to explore due to this semester focusing on our design. We want to implement our theory based on our design, what makes it strong for next semester and during the summer since we're fall graduates. So that is something I will look into. Thank you very much.
Do y'all have a way of cleaning the inside of the rover? Like if dust were to get into the railings, that would constrain the Brussels even more and not be able to move it at all?
Yes, that is true. Let me show you. If it ever looked. So whenever the solar panels contract inside, right, to allow the mechanism to rise, what we intend to be in that space in between is more of that peak polymer. Although, sure, it'll only act as a surface layer due to the dust, our mechanism is only around an hour of lifetime, which we don't expect to have much dust get inside when it's actually actualized.
Other questions?
So it kind of is an extension of what they were saying. What about the dust that gets on the brushes themselves and then enters the enclosed space?
Ooh, alrighty. Let me go back to the slide if it works. There we go. As you can see here, there's going to be these green, let me find it close up. There we go. On that second picture you see, the cleaning arm will clean itself before it goes back inside. Due to us being able to control its charge, either we will be able to attract or oppose the opposite. So whenever it gets to the cleaner section, it'll go back to neutral, so it'll act more of a regular dust. On there, it will continue to spin to clean itself off, and before it goes back to origin, it'll actually clean itself off twice. Thank you, team.
last up, we have Rel Rovers.
Hello and good evening. We are the Rel Rovers from Carleton City University. I hope you all had a good lunch and are still awake because we are going to be flying through this presentation. So meet the team, 4 mechanical engineers, 2 advisors, 1 from NASA. We have him, I'm not sure where he is, Chapman Lansdowne, and Ruben Sharifi, our advisor from Carleton. This is the agenda for today. We'll be going over our, new design for the scooter, new design for wheels, some testing, and then ending with a conclusion. And then Ethan's going to talk about the project review.
Thank you, Josh. So some of y'all might remember us from last semester. We are currently designing the Lunar Personal Electric Vehicle, the LPEV. We're keeping the same constraints we had last semester, enforcing the design challenges for range, traversability for the terrain, the safety of the rider, and keeping out the lunar dust from actual mechanical components. This was our design from last semester. This is Ultra Alpha. It's going to be a 2-wheel-based skeletonized scooter system that has a folding capability for better transportation and carry-on access. From the feedback from last semester from many groups, including Axiom, we decided to include a 3rd wheel to enhance rider stability and safety, keeping the same skeletonized design as previous semester and the folding capabilities. For this main focus of this semester, like last semester, we're focusing on perfecting our wheel. Our wheel consists of 4 major parts. 1 is the outer wheel cap, 2 is the outer wheel, 3 is the inner wheel cover, and 4 is the inner wheel hub, where the in-wheel motor will be housed. Now I'll pass it on to Swade.
Thank you, Ethan. Good afternoon, everybody. So before we start designing new wheels, we needed an actual baseline, something to base our data off of. So we started with this first wheel. This wheel is a simple wheel. It's very durable, easy to manufacture. The cons of this wheel is it's a very heavy wheel and it sinks into the regolith and it has poor traction. And due to the grounders along the contact surface, it retains a lot of that regolith, which turns into losing that traction. So here is the first design for the semester. It's going to be the straight wire mesh wheel. The pros of this wheel is it's a very lightweight wheel. It doesn't sink into that surface. The cons is when applying a 317 Newton load to the contact surface based on the average weight of an astronaut, life support systems, it does tend to fail. And due to the porosity of that contact surface, it retains a lot of that lunar regolith, which will cause wear over time. And it did have very low traction in testing. So for the second wheel design, a cross-wire mesh design, this wheel is very lightweight, our lightest wheel. It's a simple design. It passed our FBA and had acceptable traction during testing. The cons of this wheel is due to the independent cables being stacked upon each other. When that lunar regolith gets between those cables, there will be wear over time as well. For our last design, we have a honeycomb mesh. This wheel was very strong due to the honeycomb pattern, had great traction in testing. The cons is it is very heavy, a very complex surface, which leads to more difficulty manufacturing and increased cost. So here is a side-by-side of all of our 3-wheel designs. After applying the load to the wheels and using a 1.4 yield factor of safety and 2.0 ultimate factor of safety, which is NASA standard, it was found that 6061 aluminum doesn't work for these wheels. And I'll go ahead and pass it off to Silas.
Thank you, Slade. So just like last semester, this semester, the sole focus was on testing. We decided to keep our same test bed while improving it to eliminate a lot of our testing errors we mentioned last semester. I'll touch on that again in a little bit. We also decided to keep with our same quick-creep mortar mix as our simulated lunar regolith, as it really does. It really well simulates actual regolith. So this first test you're going to see here is this solid wheel, and you can really see in testing how that simulated regolith does just cake up on that wheel and cause it to sink. You can see that big pit there at the end. This wheel fails in almost every test we use it in. Up next here is the crosswire wheel. Take notice on the right of the obstacle test, how well it performs with those flexible cables.
Up next is the straight mesh wheel. Again, take note, it does do well with the obstacles, and take note of the tread pattern on the left there. And then lastly is our honeycomb wheel. Again, notice how well it does with the obstacles and the tread pattern there on the left. Here's all 4 wheels performed side by side, just so you can see a good comparison. So we ran 5 categories of tests for these wheels, and each wheel did 5 tests. So these data points you're seeing are actually an average of 5 tests with our error bars there. This is the course completion test. It's just a good overall metric of how well each wheel performs, and you can see that honeycomb wheel really does excel here. Next test is the friction test. This is just a traction test. Again, you can see that honeycomb wheel really performing well. Next is sinkage test. This is how much each wheel sinks into the lunar regolith. This is very important for us. We want no wheels to be sinking. And you can see that honeycomb wheel sinking a good amount to get traction, but not too much to where it gets buried. And then here are our slope test results. We wanted to implement these from last semester. We increased slopes at 5-degree increments, seeing at which degrees, inclines, and declines these wheels fail. You can see that solid wheel fails on almost everything, and that straight mesh wheel actually being the best performing in this category, while the crossfire wheel and honeycomb wheel perform moderately good. We're pretty happy with those. And at the end of testing, I do want to mention here that the most consistent wheel is the honeycomb wheel. We are very confident in that wheel and are happy with it as our proposal going forward. So these are testing errors from last semester. You might remember some of these. We were able to eliminate all of these testing errors except for the inconsistent density of the water mix. We just don't have the ability to mess with that right now. Here are considerations from last semester. These are all the ones we were able to implement, including the slopes of the test bed, building the prototyping honeycomb wheel, obstacles, and adding a 3rd wheel application. Here are future implementations. We want to actually get the full scooter built and tested as a full prototype. We want to implement an active braking system on the wheels, getting those implemented to the actual scooter, and testing long-term durability of all of our parts, making sure they last over longevity. I'm going to hand things off to Akash now to close us out. Thank you, Silas. We do also have some outside experiences. We were able to go to the AIAA conference held at the University of Texas at Dallas about 2-3 weeks ago, and we were able to get 1st place based on the research we've done on the wheels. A couple of quick shout outs to NASA and TAGC along with Dr. Urban for letting us come back here again and we're showing y'all what we've done with our project, as well as Charles University and Baker College of Engineering for giving us the push we needed. And I will say, we did throw a lot of information at y'all, so if y'all wanted to dig in, know a little bit more, we will be at the corner on that table, so just come by. And at this point, I'd like to open up for questions. Thank you.
Questions?
I wanted to ask, how do you include like the mass in your testing, like the mass that you would expect to have placed on the wheels, especially for the sinkage, ensuring that the ones that do pass will pass even with mass attached to them?
Great question. So on our poster back there, you can actually see on the diagram, it is in the presentation as well, but on the test bed, on our wheel arm, we have a weight platform to add weight to. Unfortunately, right as we were testing, that platform broke. We were willing to late on building a new one, so we were not able to test with weight for this semester. It is something we are obviously going to do in the future. Our pieces just broke, we didn't have time to fix them. Thank you, Vince.
So when you do test it, what do you think that the wheels are going to do? Do you think the mesh would collapse, or those cables would collapse, or the honeycomb would collapse?
We don't believe they'll collapse fully. We want them to collapse a little. So you can actually see on our prototype back there, the crosswire wheel, it has a really high arc. And what we're anticipating is happening is when you put load on that wheel, it's actually going to flatten out into more of a concave wheel shape rather than being so pointy like it is right now.
Question?
Have you considered using shape memory alloys for your metal repair?
Yes. So yes, that's exactly what we're doing. So for the contact surface, it's nickel titanium alloy, for the shape memory alloy.
and its properties, so yes.
Go back to the slide with the 4 parts of the wheel. So I saw the model you guys had over there. I saw like you want the wires to deform. Is there any worry that anybody can check with FBA? Is there any worry that if the wires do collapse, that the load would just end up being placed on the cab or the outer wheel, for example, instead of being on those meshes themselves?
Yeah, I mean, yeah, absolutely. So that's a part of that testing is making sure that that contact surface doesn't collapse too much. So we're not riding on that rim, because then of course that's going to cause damage to the wheel itself. And that's actually exactly what we kind of saw with that straight mesh wheel, as even with almost next to no load on there, it was already riding on that rim. So that's automatically excluded from our final consideration. But yeah, so absolutely, that's a consideration for our testing.
Any final questions?
We have one more over here.
All right, Ms. Simpson.
Daily cardio.
My question is in regards to the FBA. Did you have to do any nonlinear analysis to account for the contact between the wires, especially the cross mesh ones?
So I'm sure you answered the question better. Yes, we did do nonlinear FEA on the wires, since it's what's it called? Since it was a shape memory alloy, it was, yes, we needed to use nonlinear FEA. I tried to do a best with that. I'm not too experienced with the FBA, so getting into details about that, can't do too much for you, but yes, I try my best to do nonlinear FBA for that.
All right, thank you, team. That concludes our talks. Let's give all the teams another round of applause. This is our break time now. Before you go though, we really need every student team to submit their form for feedback. We don't have all of those. If you're not sure if you submitted it, check with Nina here. Also the judges, if you can finish your oral presentation forms as well as the posters during this time, that would be great. And we'll reconvene at 4:15 for the awards. Thank you.